society. Well, I think most of you know the works of Monica, but maybe not all of you know that she made a PhD in Heidelberg in the field of algebraic topology. But then, after some years, and very luckily for all of us who work in differential equations, she became interested in the field of PDEs. So she's especially interested in problems that have a variational structure and these kind of problems that you can apply geometrical and topological tools. And of course, as she comes from the field of topology, always she has a very beautiful way of studying the problems. I had the privilege to collaborate with her, and of course, I find very, very rich this point of view coming from topology. You know, I have to say that all my most difficult ideas were quite trivial for her. So, but also Monica has well, very, very rich, a very large number of publications with many different collaborators all over the world, and she published many different topics. Of course, well, today she will talk about one of these beautiful works she has done with this problem concerning critical exponent, and today she will talk about symmetries, Hopf fibrations, and supercritical elliptic problems.
Muchas gracias, Pablo, por la introducción. I also want to thank the organizers of this meeting for organizing this wonderful meeting. And well, I want to thank all of you for giving me the opportunity to share some mathematics with you this morning. So that's the title of the talk, and well, as Pablo mentioned, it combines PDE with some geometry and topology. So, okay, so this talk will include some joint results with my colleagues, Angela Pistoia and Nils Ackermann, and also with my PhD student, Jorge Falla. And the topic of this talk is to study the problem which is written there. So the PDE is probably the simplest nonlinear PDE you can think of. The domain will be assumed to be, well, omega is a bounded open set in Rn. N is going to be larger than or equal to 3. The exponent P is any number between 2 and infinity, any real number. And of course, this delta is the Laplace operator. So the first thing is, well, what do we want to know about this problem? The first question is whether the problem has or does not have a solution. And when I say solution, I always mean a non-trivial solution, because of course, u equal to 0 satisfies the equation and is 0 on the boundary of omega, okay? And then when we know that the problem has a solution, then we can also ask whether it has more than one solution. And we can also ask, what is the shape of the solutions? Are they always a positive, say, or do they change sign, or do they have some symmetries, and so on? And you see, the problem is very simplified. It depends only on two things, on the domain omega and on the exponent p. So it's also interesting to investigate what happens if we perturb either the exponent p or the domain omega a little bit. And in this case, we expect some concentration phenomena to occur. Okay, so the first thing I want to say is that the behavior of the problem depends very strongly on the exponent p. So then you can distinguish 3 cases. So there is a particular exponent which is this guy, which depends only on the dimension of the domain, which is called the critical subole exponent. And then the problem will be called subcritical if the exponent P is smaller than the critical exponent. It is called critical if the exponent is a critical exponent, and it is called supercritical if the exponent is larger than the critical exponent. Okay? So the first thing I want to mention is that in the subcritical case, this problem has been studied extensively, and one knows many things about it. One knows that the problem has infinitely many solutions. One of them at least is positive. The rest, there are infinitely many which are sign changing. And the point is that variational structure. And the variational problem, when the exponent is smaller than the critical exponent, is well understood. The negative gradient flows in a very nice way, and that's why one can easily prove using standard methods that it has infinitely many solutions. On the other hand, if you look at the case where P is larger than or equal to the critical exponent, then this is not true anymore. And in this case, the existence of solutions depends on the domain. So let me show you two extreme results. So the first result follows from an equality proved by Pogoshayev, and it says that if the domain is strictly star-shaped, then for every P larger than or equal to the critical exponent, the problem does not have a non-trivial solution. So a star-shaped domain means a domain where you can find a point in the interior from which you can see all the points in the boundary. Okay. On the other hand, if you take a ball, okay, and you take out of the ball a smaller ball with the same center, but smaller radius, then this guy is called an annulus. And in an annulus, Kasdan and Warner proved that the problem has infinitely many radial solutions for every P larger than 2. Okay? So on the one hand, we have some domains where there are no solutions, and we have other domains where there are infinitely many. Moreover, here is something that a particular behavior, which is quite interesting, because you see, if you take a ball, the ball is star-shaped, so there are no solutions in the ball. But if you make a tiny hole, as tiny as you wish, then what you get is an annulus. And in an annulus, there are infinitely many solutions. So what this is telling us is that small perturbations of the domain change drastically the behavior of the problem. Okay. So now let me, okay. This result depends on the fact that the domain has many symmetries. But this domain has also many symmetries. So what's the difference between both of them? Okay, so let me speak a little bit about symmetries. So let me call O of n the group of all linear isometries of Rn. And now let us take a closed subgroup G of this group. Okay? Take a point in Rn, and now look at the set of Gx where G belongs to G. So this is called the G orbit of the point X. So for example, if the group is the whole of On and you take a point which is different from the origin, then its On orbit will be a sphere which has center in the origin and passes through this point. On the other hand, if you take, for example, if you are in R3 and you take the group of all rotations around the z-axis, okay, then if you take a point which is not on the z-axis, its orbit is a circle, okay? And if you take a point on the z-axis, its orbit is just that point, okay? So a domain will be called G invariant if every time a point is in omega, the whole orbit of the point belongs also to omega. So the annulus is On invariant, and the torus is invariant under the action of the group of rotations around the axis of the torus. Okay? And now let me show you two results for the critical exponent. So now P is going to be precisely the critical exponent, and here one has two existence results. The first existence result says that if omega is invariant under the action of some group G of linear transformations of Rn, and every orbit is infinite, so for example, the annulus satisfies this condition, or the torus also satisfies this condition, then the problem associated to the critical exponent has infinitely many solutions. Okay? Note that the ball does not satisfy this condition, because the origin, the center of the ball, is a single orbit, and it consists of a single point. Okay? Now, the most remarkable result that one has concerning the critical exponent is a result due to Barry and Coron. So they prove that if the homology of the domain is non-trivial, then the problem always has a positive solution. Okay. So this is really a remarkable result. The proof is non-trivial, and it's all you can say, you know. I mean, one doesn't know if, for example, under this assumption, the problem has more than one solution, whether it has multiple solutions. Okay? So I will give you further on a result which furnishes some conditions to obtain multiplicity. So in a sense, these are the only two results one knows for the critical exponent. I mean, this is not really true, because one has other results for small perturbations of the domain, for example, which I will show you later on. But essentially, I mean, one knows very little about about multiplicity of solutions for this problem. Okay. But before going to that, you see, these two results are for the critical exponent. So a natural question is whether they continue to be true in the supercritical case. So if P is larger than the critical exponent, we can ask whether it is true still that if the domain is G invariant and it finite G orbits, whether as a non-trivial solution. And we can also ask whether it is true that if the homology of the domain is non-trivial, so if it has non-trivial topology, whether this problem has a solution. And a negative answer to both questions was given by Passaggio. So Passaggio showed that they exhibited some domains, omega, with the following properties. This, for every k between 1 and n-3, he exhibited a domain which has the homotopy type of the k-dimensional sphere, so its topology is non-trivial, okay? It is invariant under the group of all linear isometries in the space Rk plus 1, okay? And every orbit is infinite. And this problem has no solution for every p larger than or equal to this exponent. I will say a little bit more about this exponent. And it has infinitely many solutions for p smaller than this exponent. Okay? So what is this exponent? Okay. So first of all, each of these exponents, they are increasing with k, and they are all larger than the usual critical Sobolev exponent. And they are called sometimes, this exponent is called the k plus first critical exponent in dimension n, okay? Note that this exponent is nothing but the critical Sobolev exponent in dimension n minus k, okay? And what are the domains of Passaggio? They are very easily described. So you just take the half space in our n minus k, and you take a ball centered in the axis 0, infinity. And now you rotate this ball around this subspace. So precisely you are looking at this domain, okay? So then you see, when you take a point here and you rotate it, what you get is a sphere of dimension k, okay? And of course, this will be invariant under the action of all linear isometries in Rk+1 because of the way which, how we defined it. And these are Passaggio's domains, okay? Now you see, one can ask the following question. I mean, indeed, these domains have non-trivial homology, no? But the homology is still very poor. I mean, you have only one homology class. So you can ask whether one can find domains with richer topology, okay, for which the problem does not have, for which the problem has a non-trivial solution. Whether perhaps Barry-Coron requires some more topology if you are in the supercritical case, okay? And well, here is an answer which we obtained jointly with Jorge Falla and Angela Pistoia. We showed that for every epsilon, there is a domain omega with a property that omega has the homotopy type of a k-dimensional torus, that is of the product of k copies of the circle. It is invariant under this group, and it has infinite orbits. The problem has no solution. Well, the result is not as good as that of Passaggio because we have this epsilon, but still it doesn't have solutions above that level. And it has infinitely many solutions for p smaller than the k plus first critical exponent. So in particular, note that the topology of this guy is quite rich because we have k homology classes in omega whose cup product is precisely is non-zero. So its cup length is very large. It's k+1. Okay. So okay. So now we have seen some examples of non-existence. Okay, and our domains are very similar to those of Passaggio. Now what we take is the positive quadrant in dimension k. We multiply it with Rn minus 2k, and we take a ball with center in this quadrant. And then we rotate each coordinate separately. So the first coordinate is rotated to obtain a circle, the second coordinate the same. So what you obtain is a torus, the product of k circles, okay? But now we have to be careful. We cannot take just any ball. We need that the radius of the ball is very small, okay? So that's the role of the epsilon in the previous theorem. Okay.
So you're saying that for every positive epsilon, you can choose a domain?
That's right. You can choose a ball, but the radius goes to 0. Okay. Okay. So now I want to exhibit some domains where the problem has a solution for this k plus first critical exponent. Okay. So now we want to, I mean, we do not have results that say every domain that has, I mean, we have to find examples, okay? And these examples will give you an idea, give us an idea of the behavior of this problem. So that's the idea. So our strategy is going to be as follows, okay? So this is our problem, okay? And what we are going to do is we are going to reduce this problem to a problem which seems more complicated, okay? Because here we don't only have the Laplacian, we have an operator in divergence form, and here we have this coefficient function. But what we want to have is the following. We want that the domain omega for the second problem has smaller dimension than the original dimension omega, okay? And the other thing that we want is that the exponent p is the same in both equations, okay? So if we do that, what's the advantage? I mean, we have a more complicated equation, so we should have some advantage. And the advantage is that if you take a small p in this interval, then p will be subcritical or critical for the problem p hash, but it will be critical or supercritical for our original problem. So we will be solving a supercritical or a critical problem for a more complicated equation. That's the idea, okay? So how do we obtain a reduction like that? I will show you two ways of obtaining this kind of reduction. And the first one comes from the Hopf fibration. So that's that part of the title, okay? So what's the Hopf fibration? Okay, so you take k to be either the real numbers or the complex numbers or the quaternions or the Cayley numbers, okay? And then we take Rn to be k times k. So this means that n will be either 2 or 4 or 8 or 16. We are only in those dimensions, okay? And what's the Hopf fibration? Well, the Hopf map is given by this expression here, okay? It goes from Rn to Rn over 2 plus 1, okay? So you see, if the dimension is 4, 8, or 16, here the dimension will be smaller.
So this is kind of counting off the usual Hopf map on the sphere.
Yes, this is because I need the geometric Hopf map. I need the geometry of the Hopf map. But from the topological point of view, all you are doing is you are taking, I mean, you look at the unit sphere in K, okay? And then the unit sphere acts on K cross K just by multiplication on each coordinate, okay? And then when you look at each point and you look at the orbit under this action and you identify each orbit to a point, then this pi is the quotient map onto the orbit space, okay? But this is a topological description, and what I need is a geometric description because the main property for us will be that the Hopf map is a harmonic morphism. And what does this mean? This means that it preserves the Laplace operator. So let me show you what is precisely what we are going to use. So what we are going to need is, oops, okay. So let us take omega in k squared to be invariant under the unit sphere in k. Okay? Then we have the following proposition. An SK invariant solution of our original problem corresponds to a solution of this other problem where this theta is the image of omega under the Hopf map. So this means that theta is in dimension n over 2 plus 1 when omega is in dimension n, okay? So this is one way of obtaining a reduction. And the nice thing about the Hopf fibrations is that they do not change the left-hand side. They keep the Laplacian, okay? Of course, here we will have a function multiplying our nonlinearity. Okay. So please note that the critical exponent for the problem below is the dimension of k, this critical exponent for this problem, okay, in dimension n. So if we solve the critical problem here, then we will be solving a supercritical problem there for precisely this exponent, okay? So that's the idea. Okay, so now this brings us to consider the problem, the following problem. So let us look at the problem p hash, which is the same problem as before, but now we have this function q multiplying the right-hand side. So we will assume that the function q is continuous and positive, and in our case, the function q is this very beautiful function here, which as you can see, it's radial on x. So this is also very nice. It is a beautiful function. It has many symmetries, and okay. So this problem has a variational structure. This means that the critical points, the solutions of the problem, are the critical points of some functional, which is the one written there, on some Sobolev space, okay? And if we look at the graph of the function, we will see that it has a very beautiful graph. The graph looks like a valley surrounded by mountains. So we say then that this functional has the mountain pass geometry, okay? But, and then one is tempted, of course, I mean, using variational methods means you take a point, you follow the negative gradient flow, and you hope that it will take you to a critical point, no? I mean, if you were in a finite dimensional situation, that would happen in a picture like this. But we are in an infinite dimensional space. And in particular, when we are in the case of the critical Sobolev exponent, the trajectories of the negative gradient flow do not take you necessarily to a critical point. So that's what makes the problem hard and interesting also from the variational point of view, okay? And technically, one says that it does not satisfy the Pallas-Meil condition, okay? So what do we do? Well, one thing that is well known is that the symmetries usually help to regain some compactness, okay? And in fact, the result I gave you at the beginning for the problem when Q was equal to 1 continues to be true for any Q which is G invariant, okay? So this means if every orbit, if the domain is G invariant and has no finite orbits, then you will still have infinitely many G invariant solutions. So this is okay. But now you see that the question is, what can we say when the domain has finite orbits, okay? And well, in general, one cannot say anything because in the ball, Bogoshayev has told us already that there are no solutions, okay? So, but perhaps if the cardinality of the orbits is large enough, can we perhaps get some solutions? So let me now show you a multiplicity result for domains of this type with finite orbits, but with large cardinality, okay? So the setting is as follows. We take a closed subgroup, which I will call gamma, of the group of all linear orthogonal transformations in Rn. And we fix a domain. So we are going to fix a domain with a property that every orbit in the domain has infinite cardinality. So for example, say we fix a torus, okay? And now we are going to look where we are assuming that our Q is gamma invariant. And we are going to consider domains which contain, say, the torus, contain this fixed domain D. And now you tell me, well, I would like you to give me conditions for the problem to have 35 solutions, okay? I want more than 35 solutions. Can you give me a condition which guarantees that, okay? And, well, so the question is, given some M, under which conditions does our problem have at least M solutions in a domain theta which contains the fixed domain D, okay? And the theorem is the following one. So again, this is a joint result with Jorge Falla and with Angela Pistoia. And it says the following. It says, there is a sequence of numbers Lm. So M is the number of solutions we want to get. And this sequence depends only on the fixed domain D, the group acting on it, and the nonlinearity Q, with the following property. If you take a domain which contains D, which is invariant under the action of a subgroup G of gamma, and this inequality holds, then the problem will have at least M pairs of invariant, G invariant solutions. The first of them is positive, and the rest are sign changing. So notice that this applies in particular to our original problem where Q is equal to 1. Okay? So this gives you also a multiplicity result. And what does it say in this case? So Q is equal to 1. So what it is telling us is that it is enough that our domain has enough symmetries in order to guarantee the existence of M solutions down here. Okay? So this kind of suggests that, that in the Marie-Coron situation, we should have multiple solutions. But, well. Okay, so let me give you an example, because I think one understands these things better with an example. Okay, so say we fix a torus of revolution around the z-axis, okay? And we take Q, the function that comes from the Hopf fibration. And now let us take this GK is the group generated by the rotation of angle 2 pi over k around the z-axis. Okay? So this is a finite group, this is a cyclic group, and we have that if we take a domain which is invariant under this group action and does not intersect the z-axis, then every orbit will have cardinality precisely k. Okay? So what does our inequality tell us? So then our inequality looks like this. Okay? So if we restrict to domains whose distance to the z-axis is bounded below by some constant, by some fixed constant, then what this inequality says is that for any given m, if k is large enough, we will have m solutions. Okay? So for example, and this is very good news for babies, you know, if they have a teething toy like this one, and the teething toy has enough bumps, it will not only be soothing for the gums, but it will also carry many solutions to our nonlinear problem. Okay. So I am sure babies will be thrilled about that. Okay. And okay, and now we can go back to the supercritical case applying the Hopf fibration. Okay? So instead of giving you the general theorem, let us continue with the example. And so the example says, if you take the Hopf map, which goes from R4 to R3, okay, and we have a teething toy which contains our torus D, and K is large enough, then this problem will have M pairs of solutions, okay? Where this omega is the inverse image of the teething toy under the Hopf map. Okay? So this is one result which is supercritical. So here the exponent, this 2 star 4, 1, this is precisely 6, which is a supercritical exponent in dimension 4. Okay? Okay. And now I want to see what happens if you perturb the domain. Okay, so the next question I want to address is what happens if you have a domain, perturb it a little bit, whether you will get some results. So again, I want to apply this idea of the Hopf fibration. So this means I have first to look at the problem, at this problem, okay? And now the domain will not have symmetries. It's just I take any domain theta, I take any point in theta, and now I take out of the domain a ball of radius epsilon. Okay, so I make a tiny hole. And the question is, do I get solutions? Well, I should get solutions because you see, in the case when Q is identically 1, is the function equal to 1, so when we are in for our original problem, say, one has a very beautiful classical result due to Coron. So Coron proved that in this case, if epsilon is small enough, the problem has a solution. So this result was a previous result to that of Barrio and Coron because, of course, making a hole of whichever size generates topology. But you see, if you try to follow the Coron's proof, in the case where Q is not the function 1, then the proof does not go through. and does not go through because of the following reason. When Q is equal to 1, there is a gap, which one knows very well, where the Palais-Smale condition holds. So for the people who know what I'm talking about, between the first mountain pass level and 2 times the first mountain pass level, one knows that the Palais-Smale condition holds. But here this is not true anymore, because you see this Q, if it is not constant, it won't give us this gap. But fortunately, you know, there are other methods to deal with this problem. And here I want to mention a result that I like very much, a very beautiful result by Ge, Musso, and Pistoia. They showed that the number of solutions of this problem with Q equal 1 becomes arbitrarily large as epsilon goes to 0. And they use a different method. They use Lyapunov-Schmidt reduction. And this has the advantage that it also tells us how the solutions concentrate. So the solutions will concentrate at the boundary of the hole and will blow up at the center of the hole as epsilon goes to 0. Okay? So following this Lyapunov-Schmidt procedure, again with Angela and Jorge, we were able to prove that if the gradient of Q at the center of the hole is different from 0, then for epsilon small enough, this problem has a positive solution which concentrates around the boundary of the hole and blows up at the center of the hole as epsilon goes to 0. Okay? So then we can use the Hopf fibration and go back to the supercritical case. So in the supercritical case, what do we have? What we have is we take a point in omega, we look at its orbit under the group, under the unit sphere in K, okay? And then, so the orbit will be a sphere, and we take out a very thin tubular neighborhood of this sphere. So the result says, if the tubular neighborhood that we have subtracted is thin enough, then we will get solutions to this problem which concentrate around the boundary of the tubular neighborhood and blow up at the sphere as epsilon goes to 0. So for these particular exponents, we get a positive solution with this behavior. Okay. So now, what about perturbations of the exponent? So let me now look at the exponent. So the problem I want to study is the following one. Okay. So this is our problem. And I want to see what happens when P approaches one of these higher critical exponents we defined before. Okay? Okay. So in the case when the critical exponent is precisely the usual Sobolev critical exponent and P approaches that exponent from below, okay, we want to find, again, concentration. Okay? Then there is a beautiful result by Ray. So Ray showed that if you look at the problem for the critical exponent minus epsilon, where epsilon is a positive number, then as epsilon goes to 0, we can find solutions which concentrate and blow up at a point. So they will look like this. No? As epsilon goes to 0, the solution becomes more and more concentrated. And there are other results for sign-changing solutions, for concentration in various holes, various points, and so on. Okay. But there is another very beautiful result. What happens when P approaches the second critical exponent from below? Well, here there is a recent result, very beautiful result by Del Pino, Musso, and Packard. And they show the following. They show that there are domains for which this problem, as it approaches the second critical exponent from below, or as little epsilon goes to 0, the solutions concentrate and blow up at a geodesic, at a closed geodesic of the boundary. So you see, if you are at the usual critical exponent, you find concentrations at points. If you look at the second critical exponent, these guys have shown that there is concentration curve, but now the curve lies on the boundary. Okay? So a natural question to ask is what happens when P approach the K plus first critical exponents? So can we find domains for which this problem has solutions which concentrate and blow up at a k-dimensional manifold as epsilon goes to 0? And well, we found some examples. I will show them to you. And now I have the opportunity of showing you a second kind of reduction method. So I show you the one with the Hopf fibration. So here's another one, okay? Okay. So we are going to look at domains like the ones I showed you at the beginning. So we have the k-dimensional, the positive quadrant in RK, which is this guy, and I have some domain here, and I'm going to rotate each coordinate separately, okay? So I am looking at domains of this type. One can look at more general domains, but let me keep it simple for the talk, okay? And now, what happens? Well, if we have a function which is compatible with this rotational structure, okay, then what we have is that the solutions to our original problem correspond to solutions of this generalized equation, with A being this function, the product of the first k coordinates. But you see, this theta is the domain that is going to rotate. So it has smaller dimension than the domain where we have rotated everything. So the dimension of this is k less than this one, okay? Okay. So now we have to deal with this problem. What can we say about this problem, okay? So we are assuming now that A is of class C2, that it is positive, okay? And we will assume something else, okay? So let us look at the restriction of A to the boundary of theta. So theta is the guy who's rotating, okay? Theta is this guy. And we are assuming that it has L non-degenerate critical points with the property that the gradient at each of these points points into the interior of the domain, okay? So these points have that property. Now we can take those points and we split the set however we want. We write it as the disjoint union of two sets in whichever any way we want, okay? Then the theorem says the following thing. So this is a joint result with Niels Ackermann and Angela Pistoia, and it says the following. It says that for epsilon small enough, we can find solutions of the hash problem in dimension, critical dimension minus epsilon. So we can find a solution which has a positive peak in each point in A plus, a negative peak in each point of A minus, and as epsilon goes to 0, these peaks concentrate at the corresponding point. Okay? So if we go back to the supercritical situation, then we will obtain solutions which concentrate at tori. Okay? So let me put a picture. So here, every point, when you rotate it, it is generating a torus, and we will find a solution which concentrates with, positive layers concentrating at some tori, and negative layers concentrating at some other tori as epsilon goes to 0. So this is what this theorem is saying. Okay? Okay. Well, I'm almost done. Okay. Of course, this kind of reduction by rotation will also give us information about of solutions precisely at the level 2 star NK, so for precisely at this level. And this kind of approach, I mean, it will not always give a solution, because we have already seen the examples of Passaggio, that when this guy is a ball, or the other examples I showed you, that this not always have a solution, okay? But some results using this type of reduction have been obtained recently by Wei and Yang. So what they consider is not a ball, but a domain which has certain concavity. So it looks like something like this. So the domains of Wei and Yang are obtained by rotating something like this, which has this type of concavity here. But they do it in dimension 5 because they want that the set of minima, of global minima, contains a circle. And if it contains a circle, then they can use the finite dimensional reduction using as parameter the number of peaks in order to obtain infinitely many solutions. So this is the idea of this result of Wei and Yang. And there is also a very beautiful result by Kim and Pistoia, who also use this type of reduction to obtain solutions when you have a puncture domain theta epsilon, and then they get solutions with layers of alternating signs concentrating at the same torus, okay? So there are results of this kind. So now, what about, okay, and again, here the number of solutions grows, epsilon goes to 0. Okay, so what about the case when the exponent approaches the critical exponent from above? Okay, so here there is a very beautiful result. Due to Del Pino, Felmer, and Musso, which is it is 10 years old.